Will it be recorded also?
Yeah, it will be recorded, and also we have one dedicated, website, and we'll upload it that one there.
Okay, okay. Yeah,
So it
please
will be
share the link
always
with me
available.
also. Yeah.
Yeah, sure, sure.
Yeah.
So okay, we can start if you are ready.
I'm fine. Whenever you say, I start.
Oh, okay. So just give another 30 seconds, maybe a few of them
Fine,
are
fine.
just joining.
Yeah.
Yeah, good afternoon to all, and welcome to Air Quality Management lecture series. Go to the next slide. We started this lecture series in 2020, same month, October. So it's more than 5 years now. This is one of the important, forum in India where the young researchers, scientists, practitioners share their latest advancement in theories and applications in the area of air quality management. These lectures generally includes the recent developments, innovations, and use of recent technologies in the area of air quality management. It also provides a platform for collaboration with stakeholders and experts from various countries. Next. So these are our past air quality management lecture series speakers. Next. So we also started an air quality management association in order to reach out to the community. This we started in July 2022, again with the main aim of to enhance the understanding the science behind air quality by promoting knowledge of clean air and understanding the best work practices in the area of air quality management. So basically, we also wanted to connect the local community with professionals. So that's one of the reason for initiating this Air Quality Management Association. Next. So this air quality management lecture series was first, started with as a part of that clean environment for planetary health in Asia, where we received a fund from through UKRE project, and in this project, the aim was to enhance intersectorial, interdisciplinary engagement to co-create lasting partnership that will help instigate a clean environment transformations in Asia through innovative solutions that can provide multiple health, environmental, socio-economic benefits. So in that, we started focusing towards air quality management. Next. So we also, engaging all the professionals working in the air quality management through an international conference on air quality management. So every year it will be held in December. So this year, it will be on 10th edition. The 10th Indian International Conference on Air Quality Management will going to held from 17th to 19th December, and 15th, 16th we have a winter school. And the venue is IIT Delhi. And those who are interested, please visit our ISOCM website. Next. So I'm very happy, and it's a great pleasure. Welcome, Professor Neeraj Rastogi. And now I request Dr. Lakshmi to introduce the speaker.
Professor Neeraj Rastogi is a leading atmospheric chemist with extensive research contributions in the field of aerosol composition, transformation processes, and their implications for air quality, ecosystem health, and climate change. Professor Rastogi earned his PhD from the Physical Research Laboratory, Ahmedabad in 2005, for his pioneering work on the chemical composition of aerosols and rainwater over Western India. Following his doctoral studies, he pursued postdoctoral research at the Georgia Institute of Technology and the University of Toronto, where he investigated key aspects of atmospheric aerosol chemistry and its environmental impacts. Currently, Professor Rastogi serves as a professor in the Geosciences division at PRL, where he has made remarkable contributions towards understanding the sources, transformation mechanisms, and atmospheric impacts of ambient aerosols. With over 100 publications in reputed international journals, Professor Rastogi has been instrumental in shaping new research directions in atmospheric chemistry in India. Today's talk is titled Degradation of Atmospheric Microplastics and Nanoplastics, Health and Climate Effects. In this lecture, Professor Rastogi will discuss a rapidly emerging dimension of atmospheric pollution, microplastics and nanoplastics. These particles, now recognized as ubiquitous in the atmosphere, originate from the degradation of larger plastics into microscopic fragments and gaseous byproducts. Moreover, atmospheric microplastics and nanoplastics are not only a public health concern, but also an environmental one, influencing radioactive forcing, uh, cloud formation, and contributing to greenhouse gas emissions through photodegradation, thereby linking plastic pollution to climate change. We welcome you, sir, for the talk.
So Rastogi, you can share the slides from your
Okay,
side.
okay. Okay, so while sharing, let me thank Dr. Lakshmi for such a nice introduction. And I would also like to thank the organizer of this AQML lecture series, specifically Professor Shiva Nagendra, for inviting me to give and share whatever little bit knowledge I have gained in this particular topic. So can you see my screen now?
It's coming up. Yes.
Is it visible?
Yes.
Okay, let me go to the full screen mode. Is it fine?
Yes. Yes.
Okay, thank you. So let me start. So when Professor Nagendra wrote me an email, he says that you can choose the topic whatever you want. It should be related to air quality management and things like that. So whatever work I do means it is whether it is aerosol oxidative potential or brown carbon or secondary aerosol or application of isotopes, everything is related to air quality. But this is something which I have chosen to share. That is something quite recent we have started. So I thought let me share whatever knowledge I have gained so far. So I chose this topic. So let us start. So as we can see, the topic is degradation of atmospheric microplastic and nanoplastics, health and climatic effects. So as you can see from the title itself, initially we'll be talking about the plastics, microplastic, nanoplastic, their degradation mechanism and all, and then we will come to their health and climatic effect. Okay, so let's start. So we all know that plastic is a wide range of synthetic material made up of a variety of polymers and other chemicals as main ingredients. Their plasticity makes it possible to mold it, extrude it, or press into solid objects of various shapes, and that is what you see in the form of the single-use plastic, all these, or which is relatively long-term use, like pipes and plumbing connection and all what we use. I just chose pictures for that. Their adaptability and other properties like being lightweight, durable, flexible, and inexpensive to produce, all these properties has led to their widespread use. So you can see this picture. Any departmental store, we see variety of plastic products, and if you see in your office or home or wherever you are sitting, if you see around, there will be many things which are made up of plastic. So plastic is become a part of our life. Some more information about plastic. So this I have taken from this Zhang et al. ESNT 2025. So as of 2019, whatever they have written, as of 2019, cumulatively means around 9,200 million tons of plastic have been produced globally. About 700 million ton of this, which is about 7.6%, has been recycled, while 57.6, which is about 5,000 million tons, has been discarded. Discarded means it is lying in different places here and there. Remaining plastics are either in use, which is about 24%, or incinerated, which is about 11%. So with this info, we move forward. Okay, so this some basic information I have put, which will be useful in the slides, which I'll be discussing in later part of the talk. Please see this very carefully. So when we talk about plastic, means they are very well coded now. So there is a resin identification code. So if the code is 1, that is polyethylene terephthalate or PET. Code 2, high density polyethylene HDPE. Code 3 is polyvinyl chloride PVC. Code 4 is low density polyethylene LDPE. 5 is polypropylene, which is PP. 6 is polystyrene, which is PS. And other than that, if anything is there, that is all categorized together as code 7. And it includes all the plastics, including acrylic, fiberglass, nylon, polycarbonate, or polylactic acid, which is a bioplastic. So when I'm saying here bioplastic, except this, all the plastic, whatever we have mentioned, they are the product of fossil fuels. And this is from bio-waste. Okay. Let us see some more properties of that. So if you see the means whether they are recyclable or not, so most of them are recyclable. And if you see PET, HDPE and PS is about 30-35% recycled. Others are very less recycled. If we talk about the lifetime, how long decompose under perfect condition means they are sitting at the place where they are supposed to be sitting. So for PET it is 5 to 10 years. For HDPE it is about 100 years. Polyvinyl chloride, it says never, but there is nothing called never. That means it is very long time, thousands of years. LDPE is 500 to 1000 years. Polypropylene 20-30 years. Polystyrene about 50 years. And when we talk about these plastics, they again say never. Never means long time. And this polylactic, which is bioplastic, which is people are trying to make recently, it has a lifetime of 6 months, and that is why people are trying to switch to this bioplastic so that it degrades fast. Now if we see that what temperature they can hold higher side, so it ranges from 70 to, you see, 150 degrees centigrade. And brittlest temperature, it is from -100 to 0 degrees centigrade. So this kind of temperature they can withhold. Different plastic behave differently in different temperature conditions. Then if you see the toxicity level, so if you see this symbol, that means it is highly toxic, and if you see this symbol, that means it is hazardous. Now the last part, this is most important part. So now see this side also. The characteristics of plastics are determined by the type of polymer, which can be hundreds of chemically unique substances. Now based on the final target products, whenever you are making plastic, they often contains additives like hardeners to make the plastic hard, like BPA or BPS. This is biphenyl A or biphenyl sulfur. Then people add plasticizer to make it soft, which is phthalate ester, ultraviolet filters, which is oxybenzone, antimicrobial, which is isothioxanones. Then people add flame retardants, which is brominated organic compounds, and all these things are added in varying proportion depending upon means what you are using it. So plastics has not only these polymers but these additives also, and that is why if you see the last row, it says most commonly released toxins for different things. So for PET it is antimony oxide, bromine, diazomethane, etc., etc. For HDPE, chromium oxide, benzoyl peroxide, etc. For PVC, benzene, carbon tetrachloride, etc. Then for LDPE, these compounds, polypropylene, these compounds. So what overall I'm trying to say that plastic is not only having these basic polymers, but additives also. So there are variety of chemicals in plastic, not only the monomers which were used to make. Okay, moving further. Now, if we talk about the classification of plastic, it is classified based on 3 ways. It can be size based, shape based, or source based. So when we say size based, what it means? So if it is more than 1 meter, then we call it megaplastic. If it is between 2.5 centimeter to 1 meter, we call it macroplastic. If it is between 5 millimeter to 2.5 centimeter, we call it basoplastic. Microplastic, what we are discussing, it is ranging between 1 micron to 5 millimeter. And if it is less than 1 micron, then we call it nanoplastic. Okay. Now here onwards, we will be mostly discussing about microplastic and nanoplastics. Now if we talk about the shape-based classification, there are variety of shapes. For example, fibers which are found in diapers, cigarette filters, many garments, etc. Composition, polyester, nylon, etc. Microbeads, you are using toothpaste, face wash, etc. So all kind of things, means cosmetic products you are using, they are using microbeads. So there is a lot of microplastic in those things, and they can be PE, PP, PS, PT, PVC. So all this, now we understand this abbreviation. From last slide, we understand what is the meaning of these abbreviations. The PMMA is a new abbreviation which was under category 7. It is polymethyl methacrylate. Then you can have fragments which are found in cutlery, lids, single-use goods, etc. Again, this kind of polymers will be there. Nurdles found in plastic molds. These kind of polymers are there. Styrofoam found in cups, food containers, packaging, etc. Now means we are very fond of buying foods from outside, Swiggy, Zomato, etc., etc. Things come in this kind of containers. It has polystyrene plus additives. Now remember that slide. I will keep reminding you. Last slide. Okay. Moving further. Now source-based classification. Now for that, you can say call it primary plastic or secondary plastic. It is similar to what aerosol we talk about. So primary plastic means particles manufactured as small as less than 5 millimeter. For example, resin pellets used in raw material in plastic production, or microbeads in cosmetic products. And then secondary microplastics originating from larger species due to degradation of plastics through many pathways. What are these pathways? That we'll be talking in coming slides. And this degradation can happen in all environmental system, which is hydrosphere, lithosphere, atmosphere. Our focus today is mainly atmosphere. Moving further, so all these plastics are there. Where is the ultimate sink? So ultimate sink of plastic and source and sink of microplastic and nanoplastics. What are they? So we have seen this landfills. So all plastics, in fact, 5,000 million tons we were talking. So part of it is lying here. Then rivers, lake. So no, as a human, we are very irresponsible creature of nature, and we pollute our river like this. Glaciers. Now glacier, there is no production, but things are reaching there. And atmosphere plays a very important role in transporting plastic from source region to this glacier. Ocean, same way, ocean also, there is no source of plastic in ocean, but whatever we are producing here and there, it is ultimately reaching to the ocean. And now plastic is found not only at the surface of ocean, but at the floor of the ocean also. So although plastic lifetime is quite long, as we have seen in previous slide, they can degrade via multiple pathways and form secondary microplastic or nanoplastic. Now, since these are very small in size, they have great potential to move around in different environmental compartments. For example, it is reaching to glaciers, and they affect us directly or indirectly. What are those effects? That we will be discussing in upcoming slides. Now let us talk about the degradation pathways of plastics, microplastic and nanoplastics. So what do we mean by degradation actually? So degradation is the reduction in average molecular weight or size of the plastic polymers by various processes which weakens the material. Now extensively degraded plastic which are brittle enough to fall apart into smaller pieces. Pieces like whatever now shape we talked about, fiber, fragments, film, pellets, etc., etc. So now if you see this figure carefully, we know the meaning of mega, macro, meso, micro, nano, etc. Mega plastic can degrade to macro, meso, micro, nano all time. Macro can degrade to meso, micro, and nano. Micro can degrade to nano, and ultimately in plastic form, nanoparticle will be remaining. It may also degrade and form something else that we'll be discussing a little later. So how it is degrading? There are 4 major pathways, which is photodegradation, biological degradation, chemical degradation, and mechanical degradation. Now let us talk briefly about them. So when we say mechanical degradation, it means breakdown of polymers through mechanical stress due to external force. For example, there is a friction, means plastic is getting rubbed. So from the top layer, you will remove some part of it. There is a temperature variability. See, plastic item is lying outside your house or terrace, and daytime temperature is going to 40, 45 degrees centigrade, nighttime temperature is coming to 20 degrees centigrade. So there is a lot of temperature variability. Things will compress or expand. This continuous compression expansion ultimately make it brittle, and things break apart and form the smaller pieces in the way shown here. Then there can be photodegradation. Photodegradation is the decomposition of photodegradable molecules instigated by interaction with sunlight, mainly ultraviolet part of it. I'll be talking a little more details in the next slide. Then there can be chemical degradation. And when we say chemical degradation, it can be complete depolymerization of plastic to their monomers, or it can be incomplete depolymerization to chemicals or oligomers, plus whatever additives it has, they can also be released in the environment where these plastics are sitting. And then there is a biodegradation, which is a very complicated process by physicochemical conversion of plastic into molecules by microbes. These microbes, they look for food and easily available food. And if there is nothing, if they are sitting on plastic, then they will try to consume the carbon available there, which is a complicated process, but it is very well known that microbes degrade plastic. Okay, moving further. Now this slide is very important. Please see it very carefully. So aged microplastic or nanoplastic act as a vector of contaminants. What does that mean? So when sunlight falls on, so see, this is macroplastic, nanoplastic, and you see all P, PP, PS, PVC, SDP, etc. is written. That means any kind of plastic can be there in the atmosphere. Sunlight is falling on that. So because of photolysis, mainly by ultraviolet light and temperature variability, there can be chain reactions and cross-linking, resulting in the brittleness of the top layer of this MPs or NPs. Once it is doing this, then we know that there is a lot of many oxidants in the atmosphere like ozone or hydroxyl laticus, nitrate, etc. They can react with this MP microplastic or nanoplastic and form different functional group at the surface, like OH or this ketone group or this carboxylic group at the surface. When you are forming this group, we know that plastic is hydrophobic when you are making it. Hydrophobic is in nature. But if these functional groups are present at the surface, then you are making it to hydrophilic. That means you are changing the surface property from hydrophilic to hydrophobic to hydrophilic. That means in a way it can affect when it is there in the atmosphere, it can affect the its capacity to act as CCN or IN. CCN is cloud condensation nuclei or ice nuclei. I will be talking about that a little more. Then these toxic components attached to this microplastic nanoplastic surface via different types of bonds and interaction. Now let us go this whatever things are shown in this figure. So there can be simple cracks, and within these cracks, all these contaminants which are already available in the atmosphere, they can go and sit. There can be heavy metals, there can be anions like arsenate, chromate, there can be hydrophobic aerosol particle. So they can simply go and sit in these pores. Then there can be hydrophobic interactions between hydrophobic surface of microplastic and other hydrophobic aerosols. There can be surface complexation. So you have this functional group at the surface, and then other whatever compounds are there, they can make complex at the surface. There can be bond interaction like pi-pi interaction or hydrogen bonding. Pi-pi interaction is, means when aromatic rings are there, two aromatic rings are there. So their pi electrons, there is a interaction between them, and they can attract the other contaminants available in the atmosphere. Same way hydrogen bonding, whatever hydrogen you have, if it is coming in contact with very strong electronegative species like chloride or oxygen, it can have hydrogen bonding. So that is how it is attaching different pollutant. Then there can be simple condensation of different pollutant at the surface. There can be electrostatic attraction depending upon the charge. If they are a similar charge, they will attract. If they are opposite charge, they will repel. And also, when you are degrading it, you are actually increasing the surface to volume ratio. And when you are increasing the surface to volume ratio, that means you are giving more area available for the pollutant to reside. And pollutants like POPs, persistent organic pollutants, like this organochlorine pesticide or polycyclic aromatic hydrocarbons or polychlorinated biphenyls, and ions like arsenate, chromate, and metals like copper, iron, zinc, manganese, silver, aluminum, lead, etc., they can all sit on the plastic. So overall, what we understood so far, that when we are talking about microplastics, there is not only monomer, that means ethylene or propylene or styrene. There is additives also, plus it is having contaminants. The way it is now, by interacting with different contaminants, it is concentrating on their surface. So overall, that means if it is microplastic, so aerosol can be all kind of particles, but if this microplastic or nanoplastic are behaving as aerosols, they will be more dangerous than aerosol, because they not only themselves dangerous, but they are also containing other pollutants on the surface of them. Also, overall, if you see the environmental effect of microplastic and nanoplastic, what we see here, just a second. So what we see here, lithosphere, hydrosphere, atmosphere, from variety of sources. This whatever red dot you see, it is microplastic or nanoplastic. It comes, it goes to soil, it goes to water, it goes to air, it comes back via rain and dry deposition. But when it is in soil, it can reach to plants, it can reach to animals. Ultimately, it will coming to you. If it is going to sea, fish will be eating it, and then you are eating fish. That means it is coming back to you. If it is in the atmosphere, like aerosol, when you inhale, you can inhale and it is reaching to you. That means in whatever environmental matrix this microplastic or nanoplastics are lying, they can reach to your body. And what are the health effects, that we'll be talking a little later. So microplastic or nanoplastic present in any environmental system finally reach to our body and affect our health. In addition, they can also affect the carbon cycle in different environmental matrices. So whatever we are talking is all health point of view right now. But all plastics are carbon also, and this carbon, but it is interacting in different environments. So it, in a way, it is contributing to the carbon cycle of those particular atmospheres. So carbon cycle of water or soil or air can also be affected by microplastic and nanoplastics. Moving further, so if you, this I have taken from this Cox et al. And estimated annual microplastic particles consumed per person ranging from 78,000 to 2,11,000. This is number of particles. And how it is coming? Through bottled water. So maximum it is coming through bottled water. Then it is coming from beer. But I live in dry state, Gujarat, so I don't take this one. So you may be getting, but I am not getting this one. Then you can have plastic through air, through tap water, through seafood, through sugar, salt, honey. So whatever consumption you are doing, some microplastics are coming from these things. And ultimately, as this Cox et al. Estimated, this much microplastic is reaching to your body. And these units are, if we are talking about solids, for example, seafood, sugar, salt, then it is per gram. If you are talking about liquid like water or beer, then it is per liter. And if you are talking about air, then it is per meter cube. Okay, moving further. So let us now talk a little bit about the collection and analysis of microplastic and nanoplastics. Okay, so this is the figure from our recent review article. Just a second. Huh? So as most of you will agree, the study of atmospheric microplastic and nanoplastic is actually, it is in its infancy stage. It is growing, this field is growing. So how people do at present? So first thing is sampling. Sampling can be done in the passive form or active form. Passive means you can have funnel bottle, or you can have this collector tray, or you can have pen broom, you can collect plastic. You can have this adhesive tapes or shovel. By the way, when I'm talking about atmospheric microplastic, I'm talking about either indoor or outdoor air, or road dust, or snow, or rain. Okay, so this is how you collect passive sampling. Then means for active sampling, you can have sampler, which is pulling the air. It can have this is cascade impactor, which you can collect the size segregated plastic, and you can have low volume or high volume air samplers. So whatever way, once you have collected, then you will process it. So sieving is done in case of when you are doing road dust measurement. For aerosol, you don't have to sieve them. Weighing, in all cases you have to do. Then you do density separation. So plastic being having less density, so people use this property to separate from other particles in the sample. So people use sodium iodide or sodium chloride or zinc chloride, etc., as a solution for the density separation. Then, depending upon what other things are present, you can digest them using KOH or NaOH, HCl, HNO3, penton reagent, hydrogen peroxide, etc. To separate, you can use a centrifuge machine, and ultimately you filter it, and then it is on filter. Then this filter you are going to analyze. Now you can analyze it for different way. So, for example, initially people just did number, size, and shape. So once it is on filter, you can do visual identification, you can do microscopic evaluation, you can do this spectrophotometric study using Nile red dye staining. So this Nile red is actually a kind of dye which is get attached to the hydrophobic substances, which is microplastics. So that is how it will look like this under microscope. And if you want to do the composition, in addition to number, size, shape, if you want to do the composition also, then you have to have this micro FTIR or micro Raman or the SEM EDS or pilot GCMS, etc., etc. So these instruments are for the quantification of microplastic or nanoplastic. So whatever way you have analyzed, microplastic, nanoplastic, usually reported in the units of either number per liter, number per kilogram or per gram, depending upon what type of sample you have, number per meter cube, along with the size, shape, and composition. Typical abundances of microplastic are reported to be uh, varying from a few particles to several hundreds of particles per liter or per gram or per meter cube. Now, as studying this microplastic and plastic is highly multidisciplinary research area. Means people are working in different fields. In medicine, also people do. In ocean, people do. Variety of field people are doing. So, means there is no uniform method. So there is large uncertainty in existing reported numbers. And why this uncertainty is there? Because there are no well-established measurement protocols. Then there is a heterogeneity in sample. Say, for example, if you take soil sample, so same place, if you take two soil sample, you don't expect that both will have similar number of or size or composition of microplastic in both the sample. And so depending upon what you have collected and what other person has collected, there will be large variability. So which is causing a lot of uncertainty in ultimately, because whenever you are doing the further assessment, it is causing uncertainty in that. Further, there are no certified international standards of microplastic or nanoplastic, and there are limited libraries which are required when you do this FTR analysis or Raman analysis, etc. This table I will not go through this. It is very busy table. It is just to show how people are reporting. So at different part of worlds, you can see here different type of sample fallout, means all atmospheric only I'm talking right now, urban dust, fallout, indoor, outdoor air, etc., etc. And as I was saying, see, if it is in the form of flux, it is per unit area per unit time. If it is in the form of concentration, the number of particles per meter cube. So this is the units they are reporting. Size, if you see, it is varying from a few micron to several thousand micron. Shapes, mostly in atmosphere, fibers and fragments, that is what you observe. Color can be variety of color depending upon from where they are originating and degrading. Composition means initially many people were not doing composition, they were doing only number, size, shape, but some studies have done composition also, and you get variety of plastic there. There's polyethylene, polypropylene, polystyrene, PET. So all these kind of polymers what you see, they are getting in different samples using the instrument which I showed in the last slide, this micro FTIR or micro Raman. Okay, so this was mostly about the microplastic. If we talk about the nanoplastics, that is very much limited. Microplastic studies are limited in atmosphere, but nanoplastic studies are limited in any environmental matrix you talk about. And how to correct for atmospheric microplastic? It is in the same way as you collect aerosols, and then composition of this can be measured with this pyrolysis GCMS or a chart of AMS, and number and size can be measured with the flow cytometer. So now here I will say something which I request especially students to see very carefully. So being highly multidisciplinary field, there can be inadvertent negligence while reporting the abundance of microplastic and plastic. Usually when you see that people have reported in water or soil and they have reported 200 micron particle, 500 micron particle, so you also think that, okay, you will also be getting like that. I have seen multiple studies where people are collecting samples PM10, PM2.5, and they report the size of 100, 200, 500 micron microplastic in PM10 or PM2.5. So here we have to be very careful. We know that as an aerosol scientist, we all know when we say PM10, it means particulate matter smaller than 10 micron in size or 2.5 micron in size. So when that sample itself is less than 10 micron, you cannot have 200 micron, 500 micron microplastic in these samples. I'm just showing one example here, which means where it came up recently in scientific reports, where they have collected PM10, PM2.5 and PM1, and see the size what they have reported. So in PM1, uh, plastic ranging from 1 to 25 micron, 32%, from 25 to 50 micron, 27%. So it is not at all possible. PM1 means particle, means you have collected particles smaller than 1 micron. So it cannot have this size of particles. So please be very careful if you are doing in atmospheric sample. If you are doing microplastic, collect total suspended particulate, not PM10 or PM2.5 or PM1. You collect TSP or SPM. If you want to do nanoplastic, then you collect PM1. But once you are doing PM1, you can't have this. But at the same time, I'm sure they are not wrong in analysis. They have not thought about that. This microplastic is there in the air everywhere. So very likely this microplastic is introduced after sampling and while processing. And you thought, or whomsoever has reported, they thought that it is coming from the sample. So please be very careful, students. Okay, now moving further. Now let us talk about the climatic and health effect of microplastic and nanoplastic. Just give me a second. Okay, this is another interesting figure from our review article. So atmospheric microplastic or nanoplastic is the least studied among all environmental microplastic and plastics. Atmosphere is usually considered as the major transport pathway for the global movement of microplastic from sources to distant areas, for example, remote ocean, lakes, glaciers. So if we see in this side, we all know the sources. Means landfills, waste incineration, mechanical degradation, indoor, outdoor, agriculture waste. All these are sources. They are releasing microplastic, nanoplastic in the atmosphere. So now whatever way, once it is in the atmosphere, it is like aerosol. So it will move with the air. Wherever air is going, this will also go. And the way aerosols are removed, they are also getting removed from the atmosphere by wet and dry deposition. And via deposition, wherever this wet deposition is happening, the plastic is also coming down. Dry deposition, plastic is also coming down. So that is how it is reaching to glaciers. As I said, they are like aerosol. So as aerosol affect radiative forcing, they also affect radiative forcing. As aerosol act as cloud condensation nuclei or ice nuclei, they also can act like that. Few more things. Now plastics, people have this, I will talk a little more in detail. People have seen that degradation of plastic can also release carbon dioxide or methane, that means greenhouse gases. So the release of greenhouse gases from the degradation of plastic, microplastic, which is in the atmosphere, which is not at all studied. So I'll be talking a little more about that in the upcoming slides. Then by now we understand that when we talk about plastic, microplastic, there are additives, and then it is coming to the atmosphere. It means they can release monomers. These monomers like polyethylene, etc., they are actually VOCs. VOCs are known to affect ozone. So all these things are connected, and this microplastic, nanoplastics are aerosol. So while with inhalation, it come to our body, so it can affect our health also. So that means atmospheric microplastic, nanoplastics has a variety of effect, including health, atmospheric chemistry, this clouds, radiative forcing, etc., etc. Now we'll talk few of them before finishing the talk. Okay. So first, let's just talk about the greenhouse gas emissions from the degradation of microplastic. To best of my knowledge, I have seen these two papers only, and among the two, one is from us. So in this paper, my student Chandrima, what she did, this is the graphical abstract from the paper. What she did, she has taken glass bottles and she took this LDPE bottle, and then she made the pieces of this small pieces from this LDPE bottle, and she made the pieces in two ways. One is coarse, one is fine. When I'm saying coarse, it is about 1 centimeter. And when I'm saying fine, it is less than 5 millimeter. So this is like microplastic. So we have these pieces of plastic. We have put in different bottles. So and everything was done in triplicate. So here in 3 bottles, coarse particles are there. Here in 3 bottles, fine are there. And then we left some bottles without plastic. So that was blank. Then we also have 3 set of this, and we wrapped them with aluminum foil and kept at the same place. So that means it was not able to interact with the solar radiation. Then all this setup, it was left at the terrace of our institute building. So these bottles were exposed and they were not to sunlight, and we left that for 45 days. After 45 days, we have brought down to the lab and we did the analysis of CO2 and methane in those samples. So what we saw, see carefully, when we say C light, C means coarse, light means it was lying in the sunlight. When we say C dark means coarse, lying wrapped in aluminum foil, and blank means without any plastic, bottle without any plastic. So what you see here, that coarse dark, fine dark or blank, they are having very low concentration, more or less similar concentration of CO2, whereas coarse light was having significant concentration and fine light was almost double of that. Same way, methane also, dark, C dark, F dark, blank, they were all similar concentration, but coarse light and fine light, if you see, this fine was double of this. So concentration of CO2 and methane from the fine size fraction of LDPE was more than 2 times higher than that coming from the coarse size fraction under same natural condition. So the release of CO2 and methane from the plastic kept under dark condition was statistically not distinguishable. See this or this, which attests that whatever you see is all because of the photo degradation of plastic we kept in the bottle. So, and what else we noticed? So photochemical degradation of microplastic release greenhouse gases, which increases with increasing surface to volume ratio. So here surface to volume ratio was less, here it was more. In both the bottles, we have taken 3 gram. Okay, that I have done. So 3 gram, but number of pieces will be more in this case because the area is smaller. So that means as area to volume ratio is increasing, the release of these greenhouse gases can be high. And then and this was done with only LDPE, and we know there are wide variety of plastic. So we are not sure that how different polymers will behave if you are doing the same experiment. We will be trying that sometime in coming years. I encourage other people also whomsoever is interested, they can also try this kind of experiment. And then if you talk about nanoplastic, so nanoplastic is further very small in size. So that means release of CO2 and methane is expected to be even higher from these particles. This need to be explored. Just a second. Now, if we talk about the effect of microplastic, nanoplastic on cloud condensation nuclei or ice nuclei, there are no studies on real samples, but people have done this laboratory studies. I will show you some example. So, for example, this study came recently, 2025, and here what they did, they exposed this 100 nanometer of polystyrene particles. 100 nanometer means we are talking about nanoparticles, and they exposed to OH radical for some time, and then they measured the CCN activity. And what they found that the CCN activity was twofold higher compared to the earlier one after 27 days of atmospheric photooxidation. So what it means that aged nanoplastics are 2 times better CCN than the fresh nanoplastic. This is another study. Here what they did, then they exposed the plastic to ammonium sulfate, sulfuric acid and ozone to mimic the atmospheric condition and sunlight, and they did multiple plastics. So what are those plastics? That was LDPE, polypropylene, PET and PVC. And they noticed that the ice nucleating activities of LDPE, PP and PET decreases, whereas that of PVC increases. So what they summarized that they are non-negligible source of ice nucleated particle in the atmosphere if present in sufficiently high concentration, and they means nanoplastic or microplastics. Moving further, so this is the means everybody wish to understand how health microplastic is affecting our health. This is again figure from our review article. So this is human body. So please see this figure very carefully. So first let us see this box, what it is telling. So if circle is green, that means plastic has reached to the human body via inhalation. If it is red, that means it is via dermal contact. And if it is blue, that means it has reached via ingestion. And this is the summary of many papers. So this is not from one paper or not my study. It is just a review of multiple existing studies which we compiled, and I'm showing here. And then what else you see, if what in this box, what is the size of microplastic we got, what is the type of microplastic we got, and what are the possible health effects. So if you see one by one, so dermal effect in hair and skin, people have found plastic mostly between 100 to 500 micron. In case of hair, it can cause hair thinning or hair loss. In case of skin, it can cause skin damage or inflammatory response. Then if you see this green circle, that means through inhalation whatever has come. So microplastic has been studied in sputum and lungs. And what size? In sputum, it is from 220 to 500 micron, and in lungs, it is from 2.5 to about 2500 micron. And this type of microplastic in sputum and this type of microplastic in lungs. If we talk about the diseases, it can cause obstructive pulmonary diseases, and in lungs, it can cause asthma or inflammation. Then if we talk about these blue circles, which are many, so let us start from one side. So see, microplastic is found in breast milk. Size is 2 to 12 micron, and all these kind of particles are found in breast milk. That means it is very dangerous to infant which are fed by this, and they can cause variety of issues. Then in heart, in the range of microplastic found from 20 to 469, and this type of polymers are found, and they can cause cardiovascular diseases. Intestine from 0.8 to 1.8 millimeter, PVC, PBS, and PAPC, this type of polymers, and they can cause inflammatory bowel diseases or oxidative stress. In liver also people found from 4 to 30 micron of microplastic, these polymers, and it can cause carcinogenity or inflammation. In semen also microplastic is found, which is less than 100 micron in size, and this type of polymers were there, so it can cause impaired sperm or cervical cancer. In blood vessel, more than 700 nanometer microplastics are formed of this type, and which can cause these diseases. But this is microplastic. Nanoplastic, I'm sure there'll be many more, which I'll be talking a little later. Then in feces, it is also there in feces from 0.4 to 4.5, 4.8 millimeter, and all kind of polymers are found there, which can cause colorectal adenocarcinoma. Then in placenta also it is found from 5 to 50 micron. These polymers, it can cause fetal growth restriction, pregnancy complication, etc. In kidneys, it is formed from 1 to 29 micron. These polymers, it can cause kidney fibrosis, inflammation. In spleen, it is formed from 4 to 30 micron. these polymers, and this is the effect. And then in saliva also it is formed less than 100 micron, this type of plastics, and it can cause bacterial coagulation or different kind of allergies. This is all microplastic. Now we understand microplastic or nanoplastic, they are bioinert, you can't digest them. So they come out of our body via excretory routes only. So breast milk, feces, saliva. So these are the, and some other way, they can come through excretory routes only. Effects of nanoplastic, which are not being studied so far, can be even more dangerous because of their fine size, they can be in blood, and through blood it can reach to any part of our body. So overall, what I'm trying to say that microplastic and nanoplastic can affect health by physically sitting in different organs, or via whatever contaminants they are carrying, or whatever monomers and additives they are releasing. So all three ways they can affect, by directly by whatever they are sitting and whatever they are releasing. But if you ask the mechanism, yeah, people are still trying to understand. So mechanisms are far from understood. So now to summarize, so presently research on atmospheric microplastic and nanoplastic is in its infancy stage. There are no well-established measurement protocols. Reproducibility of measurements is quite poor due to heterogeneity in sample, especially in microplastic, as I was showing in the case of soil. Or if you take, say, if you are collecting a big aerosol filter, you will not expect that microplastic size will be same in if you are taking the alicot of the filter. If you want to do, better to use a small filter and do the analysis of the whole filter. That will be more realistic than taking the alicot and doing that. Then research on nanoplastic in any environmental matrix is just started, and there is very long way to go. So if we see, this is what we have learned, that degradation can cause mega to macro, meso and micro, macro to meso, micro and nano, uh, micro to nano, and all these by different, all of them, they can release monomers and additives, contaminants, VOCs, and greenhouse gases. And depending upon their size, the amount may be different, but they can all release this in the atmosphere, which is people are not considering, they are not studying this. So in the review article, we proposed a few things which I am listing here. So following critical knowledge gaps need to be addressed for better understanding of the implication of atmospheric microplastic or nanoplastic. So first thing is standardization of methods. That means we should develop consistent, sensitive, and reproducible techniques for the sampling, measurement, and characterization of atmospheric microplastic and nanoplastics. It is crucial for inter-study comparison and reliable global assessment. Then we should study the degradation kinetics and aging, understanding the degradation rates and byproducts of different polymers under varying environmental conditions, for example, temperature, humidity, UV intensity, etc., is actually very essential, with a particular focus on photodegradation. Then greenhouse gas emissions, release mechanisms, and pathways of CO2, methane, and other gaseous species from degrading microplastic and plastics require detailed investigation. The role of additives, binders, and coexisting pollutants in facilitating or inhibiting degradation or gas emission processes also need to be understood. Reinforcing atmospheric microplastic nanoplastic interact with the solar radiation in the same way as other aerosol does. So depending upon their size, color, and polymer composition, better estimates of reinforcing due to microplastic nanoplastics are needed. Hygroscopic properties, as we saw in one of previous slide, investigation into hygroscopicity and microphysical behavior of microplastic and plastic in the atmosphere is inevitable to understand their role in cloud and ice nuclei formation under different conditions. And health effect, as you were talking in the last slide, being bioinert and vector of contaminant, microplastic and nanoplastic may affect health in various ways. The effect of microplastic, nanoplastic, and associative additives, binders on different human organs need to be assessed. With this, I wish to thank you all for your kind attention. And if there are any questions, I'll be happy to answer.
Professor Neeraj, thank you very much for the wonderful talk. I'm sure that everybody got benefited with the lot of insight for the microplastic, which is coming as an emerging area, and many research students are definitely working in this research. Yeah, there are a couple of questions they posted in the chat box. Could you able to see them?
Let me just open that. Yeah, just a second.
Sure.
Okay. Okay, so there is a question I see by my friend Harish Galvi. He is asking, plastic is painted as villain for surviving hundreds of years in water and soil. Your research shows that they can be degraded into greenhouse gases. In that case, it should not take hundreds of years. What is your view on the rate of degradation of plastic? So probably he wrote the question before I came to the final slides where I was proposing that what research should be taken. So actually it is releasing that we have shown, but what are the rate of degradation? Those things we have to understand. So whatever way you paint, it remains not like that. It means it fades. So where that faded part is going, it is going somewhere. But we have to understand how and how much. Okay, and then it is okay. Okay, there are multiple questions actually. Let me start from the okay.
The first question I'll just quickly
Yeah,
do.
Aditi, can low cost electrochemical sensors measure microplastic?
Correct.
I'm not very sure because microplastic is behaving quite similar to the whatever samples you take. There are many other species, they are also behaving like that. So first, that is why first whenever we are doing the analysis, first we separate it from other things and then we analyze. So in my knowledge, there is no such sensor, not forget about low cost, even there is no high cost sensor which can directly give you the microplastic as of my knowledge. Yeah, and then there is a question by Angel. Uh, this question is with respect to the work published by your group. How did you prepare the course and find microplastic? Okay, so let us a little. Okay, it was simply LDP. It was cut into pieces. I suggest you means you can write me an email. I will send you the paper. Whole detail is given in the paper. So it is simply means you can read the paper. Okay, then for filter-based sampling using high volume, low volume sample, can we utilize UV visible spectrometer for detection of nanoplastic? Okay, Aditya means see when you are collecting aerosol, you know that when you are using UV visible, means light doesn't know whether it is getting absorbed by what. So first you have to separate, and then if it is microplastic, nanoplastic, so physically means you can't do that, right? So UV visible is not possible as per my understanding. You have to use FTIR or micronaman or pyrolysis GCMS kind of instrument. And then moving further, Subrata, how is the release of greenhouse gases from microplastic occurring? Additionally, how hydrophobic character is transferred to hydrophilicity in terms of plastic pollution in the atmosphere? Okay. So to answer the first, see this greenhouse gases, how it is occurring. The mechanism are not well understood. Means in our paper, we try to propose some ways which we gathered from here and there. And there is something called Nourish 1 and Nourish 2 reaction series through which people report that it can lead to the formation of CO2 or methane. But there are no established mechanism as of now. And the second part of the question is how hydrophobic character is transferred to hydrophilicity. Now, if you recall, when I was showing the aging, so I said that at the surface to photodegradation, you are creating different functional groups. Those functional groups are hydrophilic. So that is how you are converting hydrophobic to hydrophilic property, surface property. Then Ankita is asking, will CO2 methane generation potentially vary among various type of plastic? It should, means we have chosen LDPE. We chose LDPE because it is mostly used. There was no particular reason for that. Because of certain reason, means we could not continue at that time. Otherwise, we would have done multiple different polymers. But now we are planning to do. And as I said during the talk, also I encourage other people also, means please try and either validate or confront. You can confront also. No, you got, but I am not getting. Or you validate. No, you got this much, but I am getting this much. So this is how things will move forward. Okay. Then what is the methodology to do greenhouse gas accounting from microplastic? For greenhouse gas measurement, we use GCMS. Details are given in the paper. The coarse and fine plastic kept in the bottle need to be left open. No, we didn't left it open. It was closed, and that is why we put the blank also, so that there is a proper control. If it is open, then means there can be means different region for the whatever you are getting, and if it is open, then CO2 and methane will release. Means it will not stay in the bottle. Then Chaitra, while there has been growing research on the characterization of microplastic in water, soil, and air. Okay, I think I answered this when I was talking about people reporting microplastic in PM1, PM 2.5, PM10. So whatever Chaitra you have asked, probably you wrote it earlier, but I think you got the answer when I was talking about that. Then Ankush, one of the most underrated but significant source of ambient air pollution is wear particles, contain toxic chemicals like 6-ppd, 6-pptq, air opinion, relative importance of potential. See, Ankush, means you are right. So this actually, when we are talking about the wear and tear, so wear means when you are saying probably you are talking about the tire wear or non-tailpipe emission you are talking about. This people have not thought about. Means we know that when we are running our vehicles, with time tires go bad, but going bad in the process where the particles are going. Actually, they are going to different environmental compartment, including air, and through air it can reach us. So what it contains, how it is affecting means it is it is open field. There is a huge multiple things are there to study actually. So as I said in the last, it is field is open. You can do multiple things in this particular field, but do it sensibly. That is very important. Okay, Harish. So first I saw actually his question, so that I already answered. Then Divakar, how can inhalation-based studies on microplastic and nanoplastic be effectively conducted in rat models? See, when we talk about inhalation-based studies, microplastic probably may not be possible. Nanoplastic only will be possible because like rat also, they can't inhale this 500 or 100 or 1000 micron particle, but they can inhale 1 micron, 2.5 micron, 10 micron type of particle. So, as I said somewhere in the one of the slides, there are no standards as of now, but people are many people are jumping in this field, so I'm sure it will evolve very fast. But it was what I want is that it should be very well thought. We should not try to just collect a sample and report it. Try to understand and then move forward. Then Savita, surprising to know it will become hygroscopic. This will lead lung deposition, impaction on lungs. Yeah, it is surprising, but it is very well, very much possible, and this is shown by multiple studies. Means that surface properties changes with the degradation. Then Krishna Kumar, 45 days for degradation is it possible based on the rates such as 100 years are required for degradation? Okay, so whatever will happen in 100 years is not happening in 45 days. That is quite obvious. Actually, what I did, I have just put the bottles and took out after 45 days. What I should have done, that every 15 days I should have taken out and then see the curve, that whether it is linear or exponential, and then you can extrapolate that what will happen after 100 year or 50 year or whatever. Okay, he has multiple question. So how can we source identify whether microplastic is originating from different sectors such as textile, road dust, and all? So that is the reason people do composition. So once you have the composition, then you know that, okay, so for example, textile. So that means you will have polyamide in fiber shape. So shape and composition together, that will help you to understand from where actually they have come. Then which models can be adopted to get the flow of microplastic? I told you that this field itself is quite new. So model also will, I think, will be coming with time. Not in my knowledge. Yeah. Okay. Then Ariba, does photodegradation of microplastic depend on intensity of sunlight? Yes, of course. More intensity means more, means intense. More intense sunlight, that is more breaking of bonds, so more functional group you are forming. So yes, it does depend upon the sunlight. Okay, and then Lakshmi Prasad, how much time we can use syntax water tank at home? Don't ask me difficult questions. Means we have to study. So first, so once you bought that time, so for example, when you are buying it, you keep it, and then every day or every week you keep collecting sample from there, and then with time you will know that how it is degrading. Okay, and then Chaitra again, she asked something earlier, when we can collect PM 2.7 sample and later analysis them for microplastic of the particles that appears larger than the micro. See, this type of difference you can explain, say instead of 2.5 you are getting 3 or 4 type micron size particle, but you can't get 100 200 micron size particle with this sampler. Chaitra, yeah. So I think that was the last question. Anyone else? You see, you are muted, Professor Shiva. You are muted.
Professor Neeraj, thank you very much. So for answering all the excellent questions. Very useful insight informations. Thank you very much. You are extensively working on this particular topic. I have one question to understand, because I know microplastics are existing with us since we identify this, plastic bottles.
Yeah.
Do you think that several decades people are using it, and maybe we are, exposing to that significantly? The one way we are trying to see, but based on their chemical composition, they are very dangerous. But also, we are using them for, it is a part of our life system for quite a long time.
Yeah.
So how do we, look at these aspects?
Yeah. So okay, means it is very important question. Actually, my student who joined recently, she is very keen to do this exercise. We let us take the bottles what we get in the market and study them with time, that how much microplastic they are containing, because we are drinking those that water. So means, to answer your question, as microplastic is found in almost all parts of our body, so that means it is reaching. How it is reaching means we don't know. So more research is needed. But many times you would have heard that means I never drink or eat things, but I got this kind of disease, that kind of disease. We never know whether it was because of this kind of thing. That means we used to drink plastic water in plastic bottles, so something came from there. So, but means it will be hypothetical to answer. But yes, there is means very much finite possibilities that they are affecting us, and research is needed in this direction. So that was the reason why I chose this particular topic, because means I wanted to share whatever I have done so far, and let other people also try, and then let us move together forward.
So excellent, Professor Neeraj. So before we closing, I just would like to request everyone to start your camera. We will have one group photo with Professor Neeraj. Anupriya, are you taking it?
Yes, sir, I'm taking it, sir.
Okay.
Yes, sir, I've taken the picture.
So please share it with me
Neeraj,
also. Yeah.
Yes, we'll share, and we will also share the this meeting link, the recorded link to you, and this will be also available. Yeah, thank you so much, irrespective of your busy schedule, and agreed to give a talk.
Pleasure. My pleasure.
Yeah.
I hope
Thank you very much.
It was useful to all. Thank you. Thank you very much.
Yes, it is definitely useful to all the researchers. Thank you very much, sir.
Thank you. Have a nice day, everyone. Bye.
Yeah, thank you. Okay, thank you all for joining the talk. See you in the next Air Quality Management lecture series. Thank you.
Hello, sir.
Yeah.
Please go ahead.
Fatima? Yes, Fatima. Yes.
Yeah, actually, where will be that recorded?
Okay, that Professor Shiva can answer.
Yeah, all the recorded, the link will be shared, and you can also it will be posted in the group. Okay.
Okay, thank you so much, sir.
Thank you.
Thank you so
Yeah,
much.
thank you, Professor Neeraj. Thank you. Bye bye.
Yeah.
Hi, Karishat. See you.
Hi.
Hi. Happy to see you.
Yeah, nice to see you. That I come late. Seen many things. I just come back from Malaysia last night.
Oh, okay.
I went to
Yeah.
Indonesia to give a talk, a conference, and then come back to Malaysia, Kuala Lumpur, and come back to Thailand last night.
Okay. See you. I just saw your email. I think if it is an official passport, you don't require a visa, and I think it should be okay. I think you don't have to worry
Okay.
about it. But anyway, we will going to include your name for getting our Minister of External Affairs clearance. So maybe we will just put that one. So we'll include your official passport details. Okay.
Okay, I will inform you any like updated information. Yeah.
Okay.
It's quite busy period.
Okay. Thank you very much.
Okay.
Bye-bye.
Bye-bye. Thank you.
Bye-bye.
Yes.
See you all. Bye-bye.